Hello, everyone. Now let's continue our um, chapter for energy. So in previous classes, we have introduced um, some concepts of the electrostatic energies in such a system. For example, if you have electric field from the right to left, and when you put some charges, let's say positive charges in this system or in the electric field, we know the force will be the electrostatic force. And the force is pushing the positive charge from right to left. Therefore, when we talk about the energy of two charges on the left and right, we know on the right, it has higher energy because by default, a positive charge will move from right to left. It feels like if you lift some object and release it, the object will fall down, which is finding the lower energy position. When an object falls from a high position to lower position, the energy decrease. The same thing here. If you put a charge on the right side, there's a constant force, which is electrostatic force, pushing it from right to left. Therefore, when it moves from the right to left, the energy changes and decrease. And when the charge moved from the right to left, the charge is losing potential energy and it will gain some kinetic energy. And for a positive charge, the electrostatic potential energy decreases and K, which is kinetic energy, increases when the charge moves towards the negative plate or when it follows the direction of the field line. Then the potential energy or the electrostatic potential energy will be converted into kinetic energy. It's like a downhill movement. In the opposite direction, when a positive charge is moving against the electric field line, or when it's moving from negative plate to positive plate, then the kinetic energy will be decreased and the potential energy will be increased. So that's the energy conversion in such an electrostatic or in such an electric field. But if the charges are not positive, if it's a negative charge, then the direction will be reversed because the force, okay, let me use the pen, because the force, because the force on the negative charge will be from left to right. Then when a negative charge is moving along the direction of electric field lines, which is from right to left, the potential will be increased and the kinetic energy will be decreased. And if it's moving in the opposite direction, then the energy conversion will be reversed. So this figure here shows the energy diagram for positively charged particle in uniform electric field. Let's say if you have a uniform electric field, the electric field lines are from right to left. And then when you move a positively charged particle from left to right, you will see the potential will increase. However, the kinetic will decrease, but the total energy, which means the sum of kinetic energy and the potential energy, should be the same or a constant. excuse me, and we call the sum of the uh, we call the sum of the kinetic energy and potential energy to be mechanical energy, or the total energy. Okay, now let's consider two like charges, Q1 and Q2. Let's say if they're all positive charges. This is Q1, this is Q2. The electric field of Q1 pushes Q2 when it moves from X initial to X final. So this is the initial position, this is the final position. They have repulsive forces between each other, so Q1 will push Q2 to further away. So when Q2 moves from Xi, or initial, to X final, is the energy increased or decreased? The answer is decreased, because you have force in this direction and displacement is also in that direction. That means the work is a positive work. When a system is doing some positive work, then it's losing some energy. So the energy is decreasing. If we want to calculate the potential change or the work has done from Xi to Xf, we can use the equation to calculate the work. The work is an integral of F, this is F, on Q2 dx, and do the integral from Xi to Xf. And this F can be calculated by Coulomb's law, which is a constant times Q1, Q2, X squared. These K, Q1, Q2, they're all constants. So we can take them out, and then you need to do an integral of 1 over X squared dx, and the integral is from Xi to Xf. And then finally, if you know how to do the integral, you will have this number. K Q1 Q2 over Xi subtracted by K Q1 Q2 over X final. So in this case, if we define the electrostatic potential to be K Q1 Q2, then this term can be written in U Xi, and this is negative U Xf if we define the U to be in this term. Then the change in the electric potential energy of the system is delta U. It's just U I subtracted by U F. Then if we consider 2 point charges, Q1 and Q2 separated by distance R, then the potential energy could be calculated by this equation if we define U to be in this term. And this is explicitly the energy of the system, not the energy of Q1 and Q2. So if you have a Q1 and Q2, and they have a distance of R, then the energy of those two charges could be calculated in this equation. But this energy is the energy of the whole system, which contains Q1 and Q2. We cannot say Q1 has energy of this or Q2 has energy of this. We only say Q1, the system of Q1 and Q2 has energy of this term. And when R is infinity, then it becomes 0. So that means when R is infinitely far away, when Q1 and Q2 is far away, is very far away from each other, the energy could be considered as 0. And again, when R decreases, or when the distance between Q1 and Q2 is small, the energy becomes higher. Okay, now after introduced the equation of calculating the electrostatic potential energy, let's solve some problems. First of all, two like charges approach each other. Their total energy is positive. So for example, if you have a positive and positive uh, charges, and then based on the equation shown here, Q1 is positive, Q2 is positive, the X is positive, K is positive, so finally you get positive energy. And if it has some initial velocity, which is moving towards each other, then um, they will move towards each other, but their velocity will decrease and they will be slower and slower. They gradually slow down until the distance separating them is R minima. When let's say their distance is R minima, then they stop moving. The velocity of them becomes zero. So this is the distance of closed approach. So you can imagine it's like pushing two beads connected by a spring. When they move together, the initial speed might be higher and then they become slower and slower. Finally, at some point, the velocity becomes zero, but the potential energy becomes higher. There's a way to calculate the R minimum, the um, lowest or shortest distance between the two charges. Let's see how to calculate it. Okay, we'll see how to calculate it later. But now let's reverse one of the charges from positive to negative. Once they have a positive and a negative charges, if you put them here, and then they will repel each other and they will attract each other because they're opposite charges. If they have an initial velocity which is separating from each other, then they will also become slower and slower, and finally they could reach the maximum distance between them. And there is also a way to calculate the maximum distance. Okay, now another concept, which is the potential energy is independent from the path. Let's say if you have a charge, you can move it from Qi to Qf. But no matter which path you move it, either in this blue line or in this red line, the energy, let's say the energy change from initial point to final point is independent from the path. It's only dependent from the positions, because no matter which path you use, you can always do an integral to do the work, to calculate the work, and the work should always be the same. So therefore, the work done by electrostatic force depends only on initial and final position, not on the path followed. Okay, now let's solve a real problem. A proton is fired from far away at 1 millimeter diameter glass sphere that has been charged to 100 nanocoulomb. What initial speed must be proton have to just reach the surface of glass? Okay, now you have positive charge, another positive charge inside the glass, and let's say it has initial velocity so that it can move towards the glass, and it stops here, means at this position, the charge, the velocity is zero. So before it's moving, the energy of this system is kinetic energy. It has kinetic energy for this charge. After the process, the kinetic energy becomes zero. Instead, it has a potential energy, which is electrostatic potential energy. And during this process, the total energy should be the same. So we can write down